Try that. Okay, I think we're ready to get going. Got one more minute. My slides lined up here. I got Victoria twice. Lamb, you're back. I'm here on time now. Oh dear. It just isn't my day. Okay, let's get started. It's, I think, start time. Oh! So, um, oops. What happened here? Get back to my slide again. There it is. So, over the break, I hope you had a good break. Hey, it's starting to get light outdoors. It was so dark the first class I had at 11:30. It was awful outdoors. Anyway, one student, and I can't think of who it is now, sent me some photos last week. I wish others would. He wanted to send me photos of his cat Seth, and Seth is a Sphinx cat. Did I spell that right? I don't think I did. Um, But he says the cat likes quants. He likes to come and look at his computer while he's doing the quants course. Um, I don't know. Seth looks scary to me. But talking of cats, last week I tried raking some leaves, and Bruce and Sam. I introduced Bruce and Sam to you at the beginning of the course, but I don't think I brought them back. That they I was outdoors and they were looking at me out the window saying like, "Why are you out there? And why aren't we out there?" And so they both got strollers so they can go outdoors. And so here they are sitting in their strollers. Um, they aren't really good at going for walks and that sort of thing, not like a dog is. So anyway, it's our break's over. It's back to work. Bit of a struggle. Um, my brain is still on break, I guess. Lamb will be aware of that. Um, I ended my 11:30 class at 12:15, thinking that I'd run out of time. And then at 12:30, I went to start this class, and nobody was there. And I was freaking. That's why I sent out emails. You probably got an email from me saying, like, "Where is everyone? What's going on?" Uh, Lamb was kind enough to remind me, no, the class starts at 1 o'clock. So anyway, um, just one of those days. Few things before we get going. Um, that I put out an email over the weekend asking you if you missed a test or an assignment, get in touch with me about trying to get it done, and let's see if we can salvage some of the points that it's too many points that people have thrown away by missing things, and I can understand why. Uh, in total, I got 22 things I've got you doing over the whole term. And many students tell me that in all their other classes, they're doing something every week at least, and sometimes more than one item a week. Um, and so across 5 classes, you could have 50 to 100 things you have to do over the term. That's a lot to keep track of and keep track of deadlines and everything else. Um, that's something I think the university should be looking into as to how to help build a calendar for you to keep track of everything. Anyway, so if you've missed something, and a lot of people have been dealing with other sorts of health issues and other types of things, um, let me know, and let's see if we can't find a way of filling in the holes for you. I posted assignment 4. Um, at least one student in the previous class had taken a look at it, and I think she freaked when she saw how confusing it was. So anyway, the assignment I posted um, has got 3 sort of problems in it, and that they take you back to assignment 2 data, and it covers a little bit of the last bit of regression analysis that was on assignment 3, particularly nominal variables and including them. And it includes the probability that we did the last class before the break. It leaves out the introduction to classification. That was chapter, what was that, 7? 8? Chapter 8, I think. Because it isn't one I can actually get you doing an activity on. The regression, the probability you should find really easy. You should be able to do it in about 10 minutes if you understand what's going on with it. But the regression, like you had in assignment 3, regression can get very confusing, and I ask you to do lots of little steps. And I've tried to lead you through it, but it can be overwhelming with the number of little steps and so easy it is to make small mistakes or getting things not working the way they should. So as I did with assignment 3, I'll devote the beginning of next Wednesday's class to going over issues to do with assignment 4. And so what I want you to do is go and make an attempt at doing assignment 4 as much as you can without getting too frustrated. Trying to do that before Wednesday's class. And if you're running into specific questions, send me an email, or at the start of Wednesday's class, text me or use the chat to identify specific questions on the assignment that you want to make sure that I talk about um, during the Wednesday session. And hopefully we'll address pretty much all the issues that you'll hit with regression. And if you've got questions about probability, ask those as well. And once we're through your questions, then we can start in on our material for Wednesday. That we've got enough time. It's not a heavy chunk of material on Wednesday. So, but I do want you to, and as I said, I'll work through the questions with you. That there isn't a large proportion of the students that show up to class, and so I've got to give you some sort of reward for going. Anyway, we should be able to get that sorted. Oh, and one other thing that I think I've told you, I've got 2 students that work for me that as teaching assistants, and they mark your assignments. But with section C, I end up marking that, or if you're submitting stuff late, I tend to end up marking that stuff. I'm very slow about it, but I do go through and mark it. And so seeing exactly the way you're displaying some of your answers in assignments, it became apparent that there's one particular issue that has to do with when I keep asking you to give me screenshots. And so I want you to have a picture of a pivot table or of a graph you've done or something like that. And generally what I get is this great big image where the important thing is just one small piece of it. And it's almost hard to see because it's so small compared to all the other. And I'm not sure if many of you have familiarity or expertise of how to take stuff out of Excel and paste them into Word documents. And there are different ways you can do that. One of the students in the course showed me how to do it, Brandon. He used a tool that now I use all the time. So I'll be posting a video sometime later today. I'll send out an email when I get it done of different ways you can capture screen images or pieces of your screen and paste them into documents and not get surprised by it getting messed up, because there are ways of pasting it in where actually what you think you've got in there and what ends up being there are different. And I'll try to show you that in the video. But I've got to retake it. My recording of it was too clumsy. Anyway, so I'll put that up later today. I think that's it. Anyway, let's get started. So today we're doing part 2 of probability. And last time what I did was just the very basics of probability, what the language is that's used, what's the symbols, the jargon. And we've got to get through that to be able to hammer home some of the concepts associated with probability. And um, so the notation we used, the language, and this came up in the last class. There were issues to do with my use of language, and some students not understanding what I was saying. Um, some say I talk too fast, so I'll try to slow down. Um, they, it's not just language of the student in question was a Chinese student, and was, we were talking of translation and communication issues of the use of language, but it isn't um, students with a second language and that sort of thing, not of like being languages English to Chinese or Chinese to English, but the language we use in uh, the probability language I'd use or the mathematics language I'd use. Uh, Technical experts, if you go to see the doctor and the doctor speaks in medical language and the patient may not understand what that means, that we have lots of languages we use and different subject areas have their own language associated with them that often we don't understand. I've never understood what postmodernism is, in that I thought modern was current, so post would come after, but it's a term used in social sciences. I still don't understand what it means. But there are lots of terms we use that other people don't understand. Uh, if I'm confusing you with words I use, um, stop me. I guess through the chat at least, pose the questions, and hopefully I've paid attention. So with probability, there's fairly common standards in notation. We usually use a capital P to represent probability, and then we put in brackets the probability of what. And that what we'll call an event. That's what we often use, that word, event. And the event is some sort of occurrence, like buying a product. What's the probability a customer will buy our product? And what's the probability you'll say yes, or probability someone will say no? And these events we think of as hypothetical or future events. They haven't occurred yet. And so, like I gave the example of flipping a coin, the chance it's going to come up with the head facing up when I flip the coin is 50%. But after I flip the coin, that answer is either zero, it's a head, or it's not a head, it's 0 or 1. So uh, we shouldn't assign probabilities to things that have already occurred. Probability should be used only when talking about hypothetical or that sort of thing. Often we talk about it um, in that the method we use works a certain percentage of the time. Did it work in this case or not? I don't know, but um, I've got to understand what that means, okay? That either we're right or we're wrong. And I'll actually probably make mistakes in using that language in the examples we'll do today. It's really easy to. Some of the other pieces of language we have when we're talking of two events, we might talk of the probability of A and B occurring, both of them at the same time. Sometimes we use symbols for that. Or I might ask about probability of A or B or both occurring together. That and or, very, very different things. If I'm talking about two things together, we'll often call it a joint event, another piece of language. If I'm looking at someone, whether or not they buy a product, they buy the product or they're not going to buy it. One is the opposite of the other. We call that a complement. So a complement is an opposite. It's not saying something nice to you. It's it's complements are opposites, yin and yang. And so we get a formula out of that. The probability someone buys the product plus the probability someone does not buy it has to add up to 1. Probabilities should be between 0 and 1. The most you can get is 1. Lowest is 0. If it's 0, it cannot happen. If it's 1, it's guaranteed to happen. And we get a formula out of all this. The chance of A or B happening is the chance of A plus the chance of B plus minus the chance of both. because A includes both, B includes both. So, so we don't double count. We've got to take one of them out. We have a special case. It's a piece of jargon I don't like. We don't use too often. Um, if you forget it, it's generally not important. And it's called mutually exclusive. It just means that two events cannot occur together. If A happens, then B can't. So either you buy the product or you don't buy the product. If you bought it, then you didn't not buy it. It's one or the other. Um, and generally, we use that when we're trying to construct a list of categories. We want the categories to be mutually exclusive. And so if I was looking at your application into St. Mary's, and most of you are in business, a few of you are in arts, but when you applied, you had to click what program you're applying into, and you could only click one. So you could only be an art student or a science student or a business student. You could not be an arts and science student at the same time. So the chance of a new student being both in arts and science is zero. They're mutually exclusive. What happens then, though, is once you've started your program, you can add a second one. And so, although at time of admission, they're mutually exclusive, after you've been admitted, like right now, you could be a dual degree student, and they're no longer mutually exclusive. It's confusing. Um, uh, Defining categories can be often be challenging. One of the nice things, though, about mutually exclusive is how it simplifies formulas. That formula at the top of the screen here is um, complicated. You have to think about why it is you have to subtract off both. We'd like to be able to say the chance of A or B is chance of A plus the chance of B. And you can do that, but only if the two events are mutually exclusive. So if they're mutually exclusive, I can just add probabilities. And for certain types, if we've categorized things appropriately, it makes easier working out certain probabilities. I'm not sure if you need to get into that. The messier ones, but the more important ones, are conditional probabilities. It's the chance of one event happening given you know that another event has occurred. That um, that conditional probabilities are the ones that we deal with in classification problems. And most of the decision making that we make involves risks that are conditional probabilities. We have a special case of that, though, and this one is important. It's called independence. Two events are said to be independent if the chance of one happening has no impact on the other one. So um, the chance of you being successful in the course, it doesn't matter if your favorite color is green or blue or anything else, or that you were born on a Tuesday or a Sunday or any other day, that the day you were born on, your favorite color, is of no relevance in what's the chance you're going to be successful in the course. Those are independent events. And there are often we're looking for cases where events are not independent, where knowing A helps us predict B. That's valuable to us. In other cases, we like events to be independent. That comes up in part because formulas, um, we've got a formula that for working out the probability of A and B, it's equal to the probability of A given B times the probability of B. It gets a little complicated. It's hard to think through. We'll go through examples today where I'll show you how to do those without using the formula, but you are using the formula. Okay? But you don't have to think in formula terms. You can reason it out. But there is a special case if they're independent, just like if they're mutually exclusive, it makes it really simple for the addition formula. When they're independent, it makes it really simple for the multiplication formula. The chance of A and B happening is just probability of A times probability of B. That only works if they're independent. I can just multiply the probabilities together. And that helps us in certain contexts if we can make that as a simplifying assumption to make it much easier to do analysis, and it will play a role in a type of technique we'll use Monday of next week. That, um, that's another classification type approach. And again, why do we care about this stuff? Particularly the conditional probabilities. It's because we're doing classification, and the way we do classification is we're trying to predict an outcome based upon information that we know. So it's predicting outcome given the information. That's like a conditional probability. It's a conditional type of prediction. And an awful lot of classification approaches don't just say, if you're this, then you're that, type of thing. It's not a direct if then type of rule. It's a rule that works a certain percentage of the time. That if you have this thing, then you have a 90% chance of having that. And so if a transaction has certain characteristics, we might say there's a 60% chance it's fraud, or 90%, or 30%, or 10%. There are different probabilities associated with whether or not it's a valid transaction. And then based upon that probability and that risk and the consequences of that, we have a decision rule. So we do classification using a probability and a decision rule together. That the probability that we have is a conditional probability. And to be able to understand it, we have to understand some of these other probabilities as well and how they all work together. And it can be very confusing. I'm not saying it isn't. Even basic stuff, many, many, many smart people get confused with conditional probabilities. So there is a device that I find useful in thinking about conditional probability questions. And it comes as part of, I don't know if you have strategies when you're confronted with a problem. How do you start breaking the problem apart and working through it? That if you did Quant 1, you did linear programming problems. When I would teach that material, I'd get students to, there's tons of words here. You're given lots of information. But look at it sequentially and identify some things are more important than others to look at first. The very, very first thing you should be doing is figuring out what's your goal, what's your objective. That Put that down in words. The next stage is trying to decide, well, what decisions can you make? What do you have control over? What are variables that you can change? What can you change and what can't you change? What you can change are variables. Give me a list of all the things you're allowed to do. Don't tell me about the things you're not allowed to do. I want to focus on what you're allowed to do because your decision only has to do with things you're allowed to do. Then the third question I'd pose is identify what's stopping you from doing whatever you want. What constraints are on you? And then start building that. Take your problem apart to those pieces, and then you start getting into the math of building the various things. For me, that's a generic problem-solving strategy that I would use in meetings and dealing with groups. What's the problem here? And what's success to us? When we leave this room, have we come to a successful conclusion? I'll only know that if I know what the objective of the meeting was. And unfortunately, most meetings has that. People didn't know what the objective was, or they all disagreed on what the objective was. So everybody came out of the meeting being very unhappy because they had different expectations. Many meetings we spent time arguing on things that we couldn't change. We didn't have the authority to. Why are we arguing about it? We can't change it. I can't change the weather, so why should I deal with it? They didn't understand the difference between a constraint and a variable. And so anyway, we have different processes we use for problem solving. But one of the most common ones is to take very big, complicated problems and break them into smaller problems, smaller pieces. We break it apart. um, that, especially in big projects, we break it down into small pieces. But the pieces are interrelated. And so we try to show how they're interrelated, how they're connected one to the other. And an awful lot of them are connected through time. And there's a sequence. You do this first, then you do this, then you do this, then you do this. If you want to do it well, you should do them in sequence. And so understanding that linkage and sequence, we could do the same thing with probability problems because conditional probabilities suggest sequencing. One comes before the other, given da, 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 and doing it graphically that we often use when interconnecting these different pieces. We connect them in a diagram, and very often it's a tree type diagram. Sometimes it's not quite a tree. A tree has branches that keep spreading out. They don't come back together again. Sometimes our diagrams come back together again as networks, but we're going to use a tree at the moment. A tree is great for exploring things, for blowing things up. So um, I'm going to go through an example. This one's described in the chapter 9, I believe. Um, I, I found it an interesting one when I first ran across it a year or so ago. And it comes out of, I was reading about risk and how people are rational or not rational about risk, and wasn't aware that there's a whole area of psychology of risk. And there was a study done quite some time back by a German uh, psychologist, and he wanted to get a sense of how doctors perceive risk, because in making a diagnosis and giving information to a patient, um, they're using bits of information, and then, in a sense, a diagnosis is like a prediction. And did they understand chances of different sorts of things? And with diseases and like, we're always talking about risk of different things. So he tried to pick a fairly straightforward case, and I believe the doctors he was working with were fairly general practitioners. So this would be an example that they would be familiar with. And he was looking at the case of a woman that comes in to see the doctor after having had a mammogram done. And a mammogram is a diagnostic imaging test used to help detect breast cancer. And suppose the patient had a positive mammogram. And what would you say to the patient? And in particular, with this one, let's suppose it's a woman that's 40 to 50 years old, no symptoms of breast cancer, no family history. But at this stage, we've got a mammogram that's positive. And this would be a fairly common situation of this. So the doctors need some information on this and some numbers to think about and risks here. Let's suppose that 1 in 125 women in this age group would get breast cancer. I'm not sure if that's right or not, but let's suppose that's 0.8%. 1 in 125, 1 divided by 125. So it's a fairly small probability, but it's still significant. Now we've got, suppose our test is fairly reliable. If you got cancer, there's a 90% chance we're going to get a positive test result. So most of the people with cancer get a positive result. And if you don't have cancer, that 93% of the time it comes back negative. So again, it gives the right result 93% of the time. But 7% of the time, it comes back with a positive test result, even when you don't have cancer. So it could be you've got a positive test result, but you're not sick. Okay? The doctors were then asked to guesstimate, and I think they were given different ranges. What do they think the probability is that this particular woman would be one of the ones with cancer? It's what proportion of women with a positive mammogram result actually have cancer? And almost all the doctors said they thought it was somewhere in that 75% range. They thought it was quite likely. It's not guaranteed, um, but it's a very significant probability. So in his demonstration and his work with the physicians, and they had given this sort of feedback, um, he was trying to assist them in understanding probability. So let's go through and let's understand it from a probability perspective and see, is their perception valid? Because the doctors were thinking 90% of the time, if you've got cancer, it's positive, and 93% of the time, if you don't have cancer, it's negative. So almost all the time, it's giving me the right answer. So, I'll be conservative. Only 75% chance she has cancer. Okay. So it's a sequential one. First, someone has cancer, then they have the mammogram. It's not the mammogram causing cancer. So let's get this in sequence. So we'll do this as a tree. And a tree is we do branching. We start off at a root, and then we branch, and then we branch, and then we branch. And so the first branches are, do you have cancer? Do you not have cancer? And I'll put probabilities in here. If you start getting confused with this, I'm going to show you a different route. Same thing, but presented in a slightly different fashion that many students find is much easier to understand. So we'll do that. So first off, I got two branches. If there is a 0.8% chance of having cancer, then there's a 99.2% chance you don't have cancer. You've got to go down one of these two roads. These two things add up to 100%. Let's go down that. Now, let's do our test. So if you've gone down the cancer road, what's the probability you get a positive result given you have cancer? Well, they said it was 90% of those that have cancer get a positive result. So then 10% of those people must be getting a negative result. Because again, if I've come down here, I've got to pick one of these two paths. So if I go down one, then I can't go down the other. Or if I don't go down this one, I must go down the other. And you can have problems where we can branch three ways. I'm just doing two ways. And with no cancer, they said that if you don't have cancer, 7% of the time it gives a positive result. So that's going up this way. So 93% chance you go the other way. So we've got, and then at the ends of these branches are the leaves, and these represent the joint events of having cancer and a positive test, or no cancer and a negative test. Those are the things at the end. And we could calculate those using our multiplication rule. So this gets confusing. Very busy looking chart. And I'm going to show you, if this is straightforward to you, then great. But if it isn't, I'll show you an alternative. So this is what I said, 0.008 is the probability of having cancer, 90% chance of getting a positive mammogram. If I multiply the two together, that's my multiplication rule. So I multiply this by this one, I get 0.0072. A really tiny number is the probability you got a positive result in cancer. And alternatively, I got 0.0008 is the chance you got a negative mammogram and you have cancer. Very tiny number. And I calculate these. And now they're probably into numbers that make no sense to you. You may have had some gut feel for these, but these become very awkward to understand, at least for many of us, myself included. So here's the alternative way of doing it. Most students hate decimals. They hate probabilities. But frequencies, they're very, very good with. And this was an approach taken by several of my students many, many years ago. They weren't my top students, but they did very well on these problems. And this was the method they used. Since I gave you tiny decimals, they said, okay, I'll start with a really big number. I'll start with 100,000 women. So I'll start out with 100,000 at the beginning. 1 in 125 has cancer. 0.008 is the probability of cancer. So out of 100,000, that would be 800 women. So 800 women have cancer. That means 99,200 don't have cancer. So I've split the 100,000 women into two groups. Now let's split them again. I've got a positive test result for cancer patients 90% of the time, negative 10%. And if you have no cancer, it's 7% and 93. So I could take 90% of 800. I could take 10% of 800. I could take 7% of 99,200. Can't do that in my head, but work it out. So what do we get? You get 720 women have, so 90% of 800 is 720 women. 10% of 800, that's 80 women. Okay? These ones, believe me, that 7% of 99,200 is 6,944. And 93% of it is the 82,256. Big number. But now I've made it more concrete, and these are frequencies. And from there, I can work out my results. I can work out how many are getting positive diagnoses, how many have, and so on. I could summarize it in a table. Now, I've summarized this one with decimals, with probabilities. I've written them all to 5 decimal places. If that looks scary as a table, then pretend, I can't edit it on screen here, but remove the decimal and the leading zero. Here are my 720 women. Here are the 80, total of 800 with cancer. Here's 6,944 women that had positive results and no cancer. And here are all the ones that had a negative result and didn't have cancer. So adding up again to my 99,200 women, I've got 100,000 women. If I add this way, I find I've got 7,664 positive results and 92,333 negative results. So if you want to think of it as frequencies, now we're going to think about the probability. I've got a positive mammogram. I want to know, do they have cancer? 720 women out of 7,664. That's a small number. Could do it with formulas. Okay, and you don't want to do that. It probably makes no sense to you at all. But I can think of 720 out of 7,664. That's 0.094 or 9% have cancer. Here I have tests that work 90% of the time and 93% of the time, giving me the right answer. And now I'm finding that if you get a positive test result, there's only a 9% chance you have cancer. How does that happen? That it conflicts so much with what the doctors thought. Almost all of them thought it was somewhere around 75%. What took place here? Why am I getting distorted results? It's the way we interpret stuff. We're looking for something very uncommon. A lot of classification problems, we're looking for something uncommon. We're looking for fraud. We're looking for who's going to buy a product. We're looking for events that don't happen very often. We're looking for people that are going to default on their mortgage. They're generally infrequent events, but they're important ones. So it's looking for something uncommon, but the result is very valuable to us. That we've got tests that work most of the time, but the frequency of error, 10%, 7% were the two types of errors that we had. Those probabilities are much bigger than the chance of having the disease, a point less than 1%, 0.8%. So it's something that happens less than 1% of the time, and I'm using tools that make mistakes 10% and 7% of the time. That I'm using a very imperfect tool to find something very, very, very tiny. And so I'm going to make a lot of mistakes with it. That doesn't mean throw out the tool. It means in most instances, we're really filtering things. And if we're filtering, we may go through multiple filters. On the first filter, let's screen out a lot of the cases we don't need to look at. So we went from 1 in 11 women to 1 in 125. Cut it down to 10% of the of what I was looking at. So if I had 100,000 women initially I was testing, I'm down to having less than 8,000 women. Now, you may not view that as being, and it's still a lot of people, okay? And I'm not looking, and it's a small group within that I'm looking for. But then I'll do a second test, and it's going to take me maybe from 8,000 women down to 500 women. Still a large number. And maybe I need to go in third stage, and I go from 500 down to 50. Now, along the way, I'm making mistakes and so on, but that smaller and smaller group, I'll make fewer mistakes among that group if my intent is to diagnose them with cancer. I am missing some along the way. On the first screening, I'm missing 80 out of the 800 cancer cases. On the second screening, I may lose another 50. Third screening, I may lose a few. But the ones I eventually diagnose, if I'm going to do surgery on them, I'm doing surgery on people that do have cancer. Okay? We may have to drill down to it. So we shouldn't use one tool. We should probably use multiple tools or multiple inputs in classification. So don't use one input. Use multiple inputs to do our classification. Don't use just one test. But it still seems counterintuitive. Probability of a positive result given cancer is 90%, but the probability of cancer given a positive result is only 9%. It's really, really easy to get confused and get things backwards. And that's important message is to understand what is it you're trying to measure. Because many instances we get it backwards. We misstate our problem and we end up thinking it's 90% when it's really 9%, or thinking it's 9% when it's really 90%. The process of doing this with formulas, I tried to show the formula behind the scenes as we were doing it, and how did we calculate this thing. That formula can be really confusing. It gets very messy. If I expand it out altogether, it's very confusing. It's given a name. It's called Bayes' rule, after Reverend Thomas Bayes, a mathematician. Bayesian analysis is usually a term used for when you're flipping things, from going from A given B to B given A. And there are lots of problems with that. That's what we're trying to do. That we've got information that's organized one way, and we want to do what if type analyses or something, doing it the other way. Okay? I don't know if that makes sense to you, but flipping it is a very common thing. So to give you an example of how this would be coming up, this was an example from last week in an article I was reading that it had to do with the airline industry, which even this morning, I think Porter Airlines is shutting down all of its flights. I think that's what I heard. We've already seen WestJet canceling huge number of flights. Doesn't fly into Halifax anymore, I don't think. Air Canada has cut back on its flights. It's widely believed that many airlines are going to go out of business in the near future. If they go under, any resorts, think of if you had a resort in the Caribbean, Nobody's going down there for March break. Um, that that whole business is that we've got the first cruise ship operating now in the Caribbean, and they've got a COVID scare. How are we going to deal with that sort of thing? How are we ever going to get back to being able to having large groups together? And the travel industry, the tourism industry, is so heavily dependent upon it. They're hoping the airline industry has proposed that using rapid COVID tests, so not tests that take several days or a week to get the result back, but minutes to get the result back. And so you could imagine you arrive at the airport, you go to check in, and at check in and getting your boarding pass or that sort of thing, you also do a COVID test. Then you proceed over to security to go through and to get into the departure lounge. By the time you reach security, they know the result of your COVID test and they say, whoop, whoop, you're not getting in here. Said, you're positive. You go over here. And they'll screen them out. And so that hopefully then um, people that are infected won't get on the plane. But it could be it doesn't show up until later. So I think the airline industry was proposing that um, upon arrival, so they're flying Toronto to Halifax, instead of a 2 week quarantine period, they might have a 1 week quarantine period. At the end of that, they do another rapid test. And if it comes back negative, then they say, fine, you're free to go. Um, that um, it, um, you know, what it seems like a practical way of trying to do it. In Halifax right now, we've got issues to do with, although we don't have many cases, we've got a couple of clusters, and there are warnings about if you went to this restaurant, this bar, this gym, this whatever, they're worried about you having contracted the disease, and we're getting community exposure. We think what we're seeing in Europe is widespread rapid testing. In Czechoslovakia, they recently tested 3.6 million people out of a population of, or in the Czech Republic. Sorry, I'm still using old language. The Czech Republic separated from Slovakia. But in the Czech Republic, out of 3.8 million people, they tested 3.6 over a very short window of time. And so they're doing this mass screening of the population. Austria plans on doing the same. These countries plan on doing this on a regular basis so that they can get a better sense of where these pockets are in the community spread. Rapid testing could be a bit of a game changer for us, along with having a vaccine. So, um, uh, again, last week I found out one other bit that back in August, there was one of these rapid tests that was approved. Um, and Binex now, it was developed by Abbott Laboratories in the US. It was a very cheap test, only $5. It checks saliva, blood, that type of thing for testing things. And it's just like a pregnancy test. You just put it on a swab, put it on a card, and you can find out within 15 minutes if you test positive or negative. And the article I was reading was saying how often it works. It said 97% of the time it catches the positives. So if you've got COVID, 97% of the time it gives me a positive result. Good. That's better than that mammogram test. And with negatives, if you're negative, 98.5% of the time it comes up saying you're negative. So it seems like a very high accuracy rate that we get. Is this a game changer? Well, we don't know because we don't know how many people have COVID. So we could play what if scenarios. Um, Suppose 1% of the population's infected. Is that a lot? In Nova Scotia, that would be like 100,000 people, 90 to 100,000 being infected. Ooh, we don't have that many active cases. Um, but let's just suppose that if I didn't work through sketching out the tree. But if I did that with my probabilities in a tree, it would look like these things. That's confusing. Um, Let me go and do it with my frequency approach. Let's imagine 100,000 rapid tests. 1% of them have COVID. So 1% of 100,000 is 1,000. So 99,000 don't have the virus. Test picks up 97% of the COVID cases. So 971 out of the 1,000 we're going to pick up, but it's going to miss 29. It also identifies 85.5% of those without COVID correctly. So out of those 99,000, what's that? Believe me, it's 97,515. But 1,485 are misdiagnosed. Ooh, that's a lot. So from this frequency table, if you get a positive test result, well, there's 2,456 of them. What's the chance you have COVID? 971 out of 2,456. So I've got positive results happening 1 in 40 cases. Of the positive cases, 40% of them have COVID. 60% of them don't. Ooh, can you imagine yourself that coming up to security and they say, nope, you tested positive, you got COVID, you can't board the flight. That's 6 out of 10 people they stop in that fashion actually doesn't have the virus at all. What about getting on the plane? Okay, you got through, you got on the plane, and you're thinking about who else on the plane has this. If it's 1%, that's 1 in 100 people. If you're on a regional jet, maybe have 100 passengers on your flight. So without the testing, you might think, there's a chance of 1 out of the 100 people, on average, 1 out of the 100 people on this flight has COVID. I hope they're not sitting beside me. That if we're using the screening, though, that drops from 1 in 100 to 3 in 1,000. Is that good enough for you? I don't know. I'm not sure. Depends upon whether they're sitting beside me. But it's smaller. Is that a good enough risk? I don't know. But is that test good enough? It was screened out some, but I'm not sure if I'm happy either way. Maybe I'd like to have 2 tests. What if the infection rate was much lower? Say it's 1 in 10,000. In Nova Scotia, that would be like 90 to 100 people being positive. Right now, we've probably got, 20 or 30? So that may not, there may be cases we don't know about because they're asymptomatic. So if it's relatively rare, as we have in Nova Scotia, what happens now? Well, chance of having COVID, given you got a positive test result. So if they say, stop, you got COVID, you got a positive test. Well, I'm sorry, 154 out of 155 passengers that test positive are false positives. They don't have the disease. They don't have the virus. That's very upsetting if I came back with a positive test result, because I probably don't have COVID. What about the other passengers on the plane? Well, it's dropped from 1 in 10,000 on the plane. That's 1 in every 10 plane loads to being 3 in 100,000. That's pretty small. That's good. So if you're on the plane, you're safe. But I wouldn't want to be rejected from the plane. But again, we need the infection rate. And I can play other scenarios. Last week it was saying in Manitoba, 1 in 10 people that was tested came back with a positive test result. I'm presuming they were using a more precise test than this rapid test. So let's presume they really did have COVID. So if 1 in 10 is infected, um, what's the chance you have COVID given you've got a negative result. Okay, so if you're thinking of getting on that plane, okay, it's 1 in 300. It's still, that's kind of risky. Okay, I'm missing some of those positive cases. I'm worried about that. And not having COVID, given you tested positive, only 1 in 8. So 7 out of 8 people that test positive really do have the disease. That's because the disease is so common, that they, again, it all depends upon the infection rate. But we can start asking these what if questions if we're trying to evaluate a treatment. In each of these cases, I wouldn't want to make a decision based upon one um, test result. If I had a rapid test result um, using this, and it, particularly if it tested positive, I would probably want to do a follow-up test. And I probably wouldn't want to use this test procedure if I'm in a location that has a high infection rate, because I wouldn't necessarily believe um, those negative test results. I'd be worried about infected people getting on the plane. But we could start going through the scenarios and understanding this. So before I leave it, I just want to emphasize again why it's important to look at conditional probabilities versus other types of probabilities of trying to interpret things, and particularly when you're looking only at one piece of information. And this, we were only looking at one piece of information. And this comes up with Simpsons Paradox. And this is, um, you know, Simpson was a code breaker. He tried to figure out what the messages were that the German armed forces were using. Anyway, um, his main one of his, um, he wrote a paper about this sort of situation and trying to interpret patterns that you see in data that's been aggregated. And I can't remember if I used this example in the chapter or not, but this is one from, okay, it's 41 years ago, but it's still equally applicable today. So it had to do with magazine subscriptions to a particular magazine that they were looking at what percentage of subscriptions that come due. So you subscribe for a year. At the end of the year, are you going to renew your subscription or not? It's just like you subscribing to a service. That renewing your plan for your cell phone or your cable or your internet connection or certain services you're using of some sort. And they found among the customers in January, 51% renewed their subscription. But among those in February, 64% renewed their subscription. If I was in management, I'd be really excited about this. This is a huge improvement. That's a massive, massive jump. And what am I doing to be so successful? That these probabilities, these are relative frequencies. This is historical data. These aren't real probabilities in the sense of going forward unless we think this reflects the future going forward. And that even if all conditions stay the same going forward, um, because it's based upon sample data, my estimates are not precise. There may be some error because of the sample size. But these sample sizes are huge. So these numbers are fairly accurate. I wouldn't worry about, estimation error. It wasn't 51 versus 64 because you only looked at a small number of cases, like opinion polls and we just had an election with opinion polls where people are arguing about the accuracy of them. And part of the errors in the polls about uh, voting for Trump versus Biden had to do with how big a group they surveyed and whether or not they're representative. So uh, they aren't all that accurate. But anyway, these ones, accuracy isn't an issue. Um, and so based upon what we've seen, we should look at what did they do in February that was different from January to make them so much more successful, and find whatever that is and keep doing it. And but to do that, you may have to drill deeper into your data to see what was different. And this is where I pick up not just January versus February, so probability renew given January, probability renew given February, but add a second variable, like a second test, that because the first one may not tell the whole story, just like these virus tests don't tell the whole story. And you have to look at where did these customers come from? And with subscriptions to a service, they often are recruited through different channels. And just like people that take up a cell phone subscription or internet or whatever, they buy it in response to different sorts of things. And with magazine subscriptions, some small number get it as a gift at Christmas time or something. That used to be a common sort of gift, would be to buy a subscription to things. Um, some, well, they were previous subscribers and they just renewed it again. So they're loyal customers in that regard. Some responded to a direct mail marketing campaign. It used to be common practice with magazines to subscribe through a subscription service where you bought a package of things, a whole bunch of things at once, and you got big discounts and that type of thing. And the and then there's a catalog agent, and I'm not sure exactly what that one is. I can't think offhand. But there are different channels and different volumes of traffic through different channels. And if you look at how those things came due in different months, you'll see that an awful lot of subscribers renew in January, and particularly those that got it as a gift or that um, it was a previous subscription they carried, that type of thing. Um, but you'll notice that those in February, almost none of them are through things like subscription services and so on. And the renewal rates are different for different services. If you get it as a gift or you're a previous customer, there's a very high probability you're going to renew. If you got it through a subscription service, it's a very low probability you'll renew. And the mix of different things, different ones, when we broke it down by channel, you'd find renewal rates declined in every channel. So I've got an increase in renewal rates from month to month overall, but a decrease in renewal rates in every channel that's happening. So it's very contradictory. This is Simpsons Paradox. Just warning you again, think of that extra variable. We talked about this when we were doing pivot tables. And if you start seeing a pattern in your table, if you've got enough data, like in this one, there was enough data, drill down deeper and see, is there another variable that's important there as well? Because you don't want to be misled in your predictions that you're going to be having. And very often when we're building our decision models, when we're building our classification schemes, we're going to use more than one variable. Just like with diagnostic testing, use more than one test before you make your conclusion. Don't jump to a conclusion. Anyway, so what's coming up next? Well, next class, I promise, I'll be spending a good chunk of time on assignment 4, presuming that you're interested. I hope you are. And they, oops, hold on. Seems I go over here and if I go to chat, it changes things. But the other 2 things I want to cover in Wednesday and Monday of next week, and neither one should take us too long to cover, are 2 ideas for how to do other types of classification. One is this idea of trees. Taking my data, splitting it, taking my data, splitting it, and splitting it, and splitting it, and doing it like in a tree. And what I'd like to do is then find groups that are all the same at the end of the tree. If as I branch out on the tree, the leaves at the end, I want all to be cancer patients or all to be those without cancer. All of those that are going to buy the product and all those that are not going to buy the product are in these nice little pods at the end. Okay? And um, the tree sort of gives me that idea of maybe splitting things in that sort of way. The other is this idea of Bayes, of flipping things backwards. Turns out to really do that in complex problems, the math gets horrible. But if I make some assumptions about independence that may not be true, but are convenient, can I come up with some decision rules, sort of probabilities um, that will give me an idea of, are you likely to buy it? Are you not likely to buy it? Are you likely to renew? Are you unlikely to renew? And these two strategies are both ones that are in very widespread use. And they come out of the type of reasoning we've had today. And so I'd like to get into them just as other ways to start thinking about this. Again, they're ones that it's awkward for me to give you assignments and things to do to work through this. Um, Not sure if I will or won't be able to do this on an assignment, but we could do some of these in a manual sort of fashion a little bit. And I'll show you about that in the next class. But after we go through the questions you may have on to do with your assignments. So that's where we leave it today. Um, I hope this has been useful to you. I think you're all still about here. There are about 12 of you, I think. Anyway, you have a good day, and we'll be in touch again on Wednesday. Between now and then, please try assignment 4. And if there are specific things you want me, parts of the assignment you would like me to go over on Wednesday, if you can give me a heads up, that would be great. If you don't think about it until Wednesday at class time, at the beginning of the chat session, if you would post your question, I'd much appreciate it, and I'll ensure that I go through that. And we'll do it as a live type of session like we did with assignment 3. So you take care, and oh God, I'm actually seeing blue sky. Maybe we will have a nice day after all. Bye now.